Have you ever just stopped and wondered what is actually happening inside an AI when you hit enter? It feels like magic, right? Well, today, we're going to pull back the curtain. We are going on a journey following a single prompt from your screen deep into the core of an AI and all the way back out again. So, picture this. You type in a question, and just moments later, a perfect answer pops up. But what happens in that tiny gap? That's what we're going to unpack. We're going to trace the path of your words as they transform from human language into the mathematical heart of a modern AI, and then see how it all comes back as a coherent thought. It's an incredible trip. All right, so the first and most important thing you've got to get is this. A large language model isn't one single giant brain, not at all. It's much more like two distinct parts, two minds working together in perfect sync. On one hand, you've got the algorithmic layer, which we're going to call the orchestrator. Think of this as the clever planner, the one that prepares everything, interprets the situation, and makes all the key decisions. And on the other hand, you have the computation core, which we'll call the engine. This is the absolute powerhouse, holding all the knowledge and doing all the heavy computational lifting. So the orchestrator? It's basically the project manager of this whole operation. It's juggling your chat history, formatting everything just right, and, this is crucial, it's deciding which word the AI should say next. Plus, it's got a few really neat performance tricks up its sleeve to make the whole conversation feel snappy and smooth. We'll get to those later. The engine, meanwhile, is where the real deep magic of the transformer architecture lives. This is where billions and billions of parameters are stored. That's basically the AI's entire library of learned knowledge. It runs all the complex calculations that let it actually understand language. All the training, all the learning, it all happens right here, in the engine. Okay, so we have our two minds, the clever orchestrator and the powerful engine. Let's start with the orchestrator. How exactly does it take your simple question and get it ready for the engine to process? Well, it's a four-step process. First, it takes your raw text and wraps it in a chat template, adding little labels like user and assistant to keep track of who's talking. Then, your text gets broken down into these numerical pieces called tokens. And finally, those tokens are converted into what we call embeddings. These are rich mathematical vectors that actually capture the meaning of the words. That's the stuff the engine can really work with. So, what exactly is a token? Honestly, the best way to think about them is like Lego bricks. They're the fundamental building blocks of language for an AI. A special component called a tokenizer scans your sentence and breaks it down into these pieces. Sometimes they're whole words, sometimes just parts, and it gives each little piece its own unique ID number. Now here's a cool part. Not all tokens are actually words from your prompt. Some of them are special control tokens. They're like invisible instructions for the AI. You'll have one that says start of text and another like quote, end of prompt, which basically tells the model, okay, the human's done talking, it's your turn to reply. These are absolutely essential for managing the flow of the conversation. All right, the prompt is now prepped, tokenized, and embedded. The orchestrator hands it off, and now we dive deep into the heart of the machine itself, the computation core. So, inside the engine, everything revolves around this concept called the residual stream. Just picture a shared digital whiteboard. As your prompt moves through the many, many layers of the neural network, each layer reads what's on the board, adds its own calculations and insights, and then writes its updated findings back onto the board for the next layer. It's this continuous collaborative process of refinement. And the scale we're talking about here is it's mind-boggling. An engine like the one we're looking at might have 117 billion parameters. You can think of each parameter as a tiny little knob that's been perfectly tuned during training. Altogether, they represent the vast ocean of knowledge the AI has learned. But here's where it gets really clever. The AI doesn't actually use all 117 billion of those parameters for every single token it processes. No way. Thanks to an architecture called Mixture of Experts, or MOE, it intelligently routes each token to just a small group of specialized experts. This means only about 5 billion parameters are actually fired up at any given moment, which makes the whole thing way more efficient. Now, the engine works in two very different modes. First is the prefill phase. This is where it reads your entire prompt all at once in one massive, parallel burst of computation. It's super fast. But then it switches to the decode phase to write its reply. And this part is serial. It generates the response one token at a time. This is a much slower process, and it's why those performance tricks we mentioned earlier are so important. So the engine has done its heavy lifting. It's crunched the numbers, processed the prompt. Its work is done. The results of all that computation get sent back upstairs to the orchestrator, which now faces the most important decision of all. What word comes next? What the engine actually sends back is a giant list of numbers called logits. There's a logit score for every single word the AI knows, tens of thousands of them. You can think of this list as the model's raw gut feeling, its instinct about which words would be the best fit to come next in the sentence. The orchestrator then has to use a decoding strategy to pick a winner from that list. The simplest way is called greedy decoding. You just pick the word with the absolute highest score. It's fast, but it can make the AI sound really repetitive. A much more common approach is sampling, where it basically just picks from a small group of the top-scoring words. This adds a little bit of randomness, and that's exactly what makes the AI's responses feel so much more creative and human-like. I absolutely love this analogy from the source material. It says to think of the engine as a factory that produces lottery tickets, where every ticket is a possible sentence. The training process, especially reinforcement learning, doesn't try to pick the winning ticket. Instead, what it does is it tinkers with the factory machinery so that it just naturally produces more of the kinds of tickets that humans think are good.
Okay, so remember how we said that the decode phase, generating the response one word at a time, is actually pretty slow? So why do conversations with an AI feel so fast? Well, this is where the orchestrator pulls off some of its most clever tricks.
And the biggest trick in the book is called the KV cache. This is basically the engine's short-term memory. Remember that super fast pre-fill phase where it read your whole prompt? The orchestrator tells the engine to save all the key calculations from that step. That way, when it's generating the next word and the next and the next, it doesn't have to go back and reread the entire conversation from the very beginning every single time. This one optimization is an absolute game changer. It massively cuts down the amount of work needed to generate each new token, turning what would be an impossibly slow process into something that feels like a real conversation. This is what makes those long back-and-forth dialogues with AI even possible. So you see, it all comes down to this really elegant separation of duties. It's not just one magic box, it's a powerful partnership. Let's just quickly run through that whole journey one last time. And that really is the main takeaway here. The incredible power of modern AI comes from this partnership. You have the smart, efficient, algorithmic orchestrator managing the whole workflow, and then you have the massive, knowledgeable computation engine providing the raw intellectual horsepower. Neither one could do the job without the other. Which leaves us with a really fascinating question for the future. As these systems evolve, what's more important? Should we focus on building bigger and bigger engines, packing in more and more raw knowledge? Or is the real progress going to come from designing smarter, more efficient orchestrators with even more clever tricks? The answer to that is probably going to shape the next generation of AI.